Hello, I'm Kevin Buzzard, and this is the solutions to the monster sheet 3 of section 6 quotients of my Formalising Mathematics 2022 course. So we've defined Z mod 37, and I was going to prove theorems about it in a Z mod 37 namespace, but to my mild surprise you don't seem to be allowed numbers in namespaces. So everything's happening in Z mod. The first thing, remember we defined neg in the last video. See, zmod.neg is a function from Z mod 37 to itself. But we want to use normal notation for it. Like if I do variable a in Z mod 37 there, and then I do check minus a, Lean is like, I don't know what that means. Right? Lean says, what's this weird minus sign in front of the a? I don't know what that notation means. So we could do neg a. That works fine, right? Neg a is just still an element of Z mod 37. But the notation for negative is not there yet. And so that's what this instance does here. This is a notational type class. And if we try it again after there, you see now it works. Now it says negative a is in Z mod 37. So that's what's going on with this instance thing. So now we can talk about negation, and I thought I'd try training the simplifier. I don't really know if this is a good idea or not, but I thought I'd try and train the simplifier to push everything into brackets. So for example, negative equivalence class of a is equivalence class of negative a. This is true by definition. But I've made it a simp lemma. So similarly here we don't have a 0. We could check 0 in Z mod 37 there, and that says I've got no idea what 0 means. And then if we try it after that line there, it still doesn't know because I've spelled Z mod wrong. But there we go. There it does work, and there it doesn't work. Okay, yeah, that looks better. And in fact, you get when it doesn't work here, it complains it says exactly what the problem is. It says the type class inference system cannot find a term of type has 0 Z mod 37. So I make a term of that type, and I tag it with the instance attribute. And there's a quick way of doing that by just writing instance. And I say 0. Why don't we make it the equivalence class of 0? You know, that would be a sort of a sensible thing to do. So now we've got a 0, and indeed 0 is by definition the equivalence class of 0, and that's true by definition. So now the next thing is addition. And addition, so we need to go back to quotient. Remember I talked in the last sheet about quotient.lift and quotient.map. So I'm going to use quotient.map here because why not? And in fact, I'm going to use not quotient.map, I'm going to use quotient.map2 because addition takes 2 inputs, right? That's what's going on there. So I use quotient.map2, and now this is a function on the integers, sending a and b to a plus b. You can see they're integers. I hover over them, you see, and it says a is an integer. I don't actually know if you can see that on the video, but whatever. I can. If I put my cursor on that a, I get a little pop-up saying a is an integer. So there's quotient map to begin. So I'm going to have to prove some. I think the lemma I'm going to have to prove is something like if a is congruent to a prime mod 37 and b is congruent to b prime mod 37, then a plus b is congruent to a prime plus b prime. So it looks like a complete mess, but let's assume that that's what Lean's asking us. So let's do intros a1 and a2. And then H, A, and then B1 and B2. Let's rintros it because we've got to get a lot to get through. So this is whatever X, H, X, and then B1 and B2, and then Y, H, Y. And now what does this thing say? Aha! So now we've got to prove. So this is A1's related to A2 and B1's related to B2. We've got to prove that A1 plus B1's related to A2 plus B2. This is a question about integers. So we're going to use X plus Y, right? So we don't need to descend. We can probably just use X plus Y. We could do refine X plus Y, comma, underscore, because refine is actually the use It's decent, but it's still a mess. So now what we've got to do, we want to use 37x and 37y. So I guess what we should do is we should just rewrite distributivity. We should rewrite malad. Maybe we could get the simplifier to do this. We could do simp malad. If I do that, yeah, so that does it. And now we need to do hx, left hx, and that does that. And now left hy. Oh man, it doesn't do it. Rotten luck. So now, okay, bring out the big guns. Just use ring. Hard luck. There we go. My cat wants to get into my shed. I think I'll leave her outside. And so now I will. So now that's addition defined, and so now we've got notation for addition, right? So, example. Do you know what? She's going to drive me nuts. Just let me let my cat. Oh, let me let my cat in. Hang on. I can't believe this. Very unprofessional. Come on then. Yes, yes, yes. Happy now? So this is another notational type class. We're defining addition. You see, this wouldn't have made sense before. If I comment this out, then you see this lemma doesn't work. It's quite happy to add the integers. That's addition of integers. A and B are integers, but it won't add integers mod 37. I could do it with the add function, but I can't use the add notation until I do this. So there we go. That's now working fine. And now I've got to show you the one last trick, right? How do we actually prove things like z plus 0 is z? So this is kind of, if you keep your head, you can kind of see what's going on here, right? First of all, we've just got questions about something mod 37. There's no integers here at all, right? Z is an integer mod 37. And yeah, now she wants to go out again. I should never have let her in. We've just got a question about integers. We'd like to get some integers involved, and the way to do. Obviously, z mod 37 is the quotient. This z is an equivalence class, right? We can write it as the equivalence class of a for some a, but we don't have the a yet. And the way to get the a is quotient dot induction on. So I apply quotient dot induction onto z. And I get that. And now this is still a question about z mod 37, but there's an integer. And also, do you see, we have this z, but it's not mentioned anywhere. Z is now sort of irrelevant, so I've cleared it. And now this is a question about integers for all a and z. A plus 0 is a. I don't believe this. You're not coming back in again, right? Terrific. Where was I? Oh yeah, so now we've got an integer, so now we can do intro a. But now this is still a question. This is still a question about z mod 37. So what we'd like to do is apply something like, do you remember quotient dot sound? Let me just save this and pop over to here. Where did I show you quotient? It probably wasn't. It probably was in sheet 2. Yeah, see, quotient dot sound says if A is related to B, then equivalence class of A equals the equivalence class of B. So that's the kind of thing we might want to use to try and get out of this. Z mod 37, right? We don't know anything about Z mod 37 at the minute. We're just creating all the structure on Z mod 37. So it would be nice if we could get to the integers. But let me just explain to you what's going on here. By definition, that 0 is a equivalence class of 0, right? So we could do change a plus 0 equals a. You see that's true by definition. And this a plus 0, remember this this add def here is also true by definition, right? Quotient a plus quotient b is quotient a plus b. So we could even do this, right? We could do change a plus 0 like that. Yeah, that's also true by definition. So the goal is definitionally of the form quote equivalence class of x equals equivalence class of y. So apply quotient.sound works there, and it, you see, and it replaces it with, you know, it turns equivalence classes are equal into things are related. So that's one way of doing it. And then I guess the simplest way of fixing this, now I could rewrite add 0 here, you see. Yeah, that solves the goal. But I've been training, did you notice I've been training the simplifier, like as well as these things being true by definition, I've been training the simplifier to do it. A plus b is a plus b, and sort of 0 is 0. These are all simp lemmas. So you can train the simplifier to do it instead, and you see simp actually solves this goal completely. But for add com, you see, add com was, I think we might not be so lucky. So add com y plus z equals z plus y. So it's the same strategy, right? This time you apply quotient induction on tiny little 2. You get that with sort of \2. And then intros. And then, so now we could try the simplifier. You see, the simplifier doesn't do it. But I guess actually if we told the simplifier about add com, yeah, you see. So isn't that funny? We were trying to prove add com, but we somehow solved it using add com. So that sounds a bit circular, doesn't it? So it's a bit dodgy. It looks like something dodgy happened. But what's happening is we're trying to prove add com for integers mod 37, and the simplifier will get as far as reducing it to a question about integers. You see, a and b are integers here. If I click on there, that addition is has add z, right? On the integers, and so add com for the integers is fine because we're using lots of facts about integers. That's fine. So that's the proof of that. Do we even need intros? Yes, we do. Okay, so now let's knock these things off. Add a sock. I guess we do intros. We do intros, and then we do apply quotient induction on 3, I suppose. There we do /3, and what did I call them? A, B, and C. A, B, and C, and then we can clear A, B, and C. And now what have we got to prove? Well, let's see what the simplifier does. Great, the simplifier. Okay. I think we might have to do the intros. Well, let's try simp. Let's try simp. What is this? Add a sock, right? Yeah, that's a shame. Intros, simp add a sock. There you go. Yeah, it does it there. Somehow. I see this. I see the simplifier knows that those 2 squiggles are an equivalent. That's a shame. The simplifier knows that this is an equivalence. That equivalence relations are reflexive, but it won't solve it because somehow it's under the binders. There we go. And 0 add. So it's going to be the same pattern, right? Where's add 0? So it's probably intro Z there, and then let's try intros simp. That does it. There we go. Add 0 we've done already. That proof there means the proof of add 0 for Z mod 37 is just the add 0. Those 2 add 0s are completely different. That's the name of the axiom. That's the name of the theorem we proved, right? If I change add 0 to add 0 q, then this would break. And the thing that breaks, right, and I can't change that q there because now I get some error about, I've never heard it, yeah, add 0 q is not a field of this structure. So we fix this by putting that there and then putting the add 0 q, right? That's what's going on there. I don't want to call it add 0 q, let me fix it. There we go. Now what have we got to do? Add left neg. So again, let's try, that's got 1 variable, so let's try that. And then let's try intro simp, and that works fine. And now what? So now so now we've proved it's a group, right? Now we've got a term of type adcom group Z mod 37, which means we've got so adcom group 37 is the type of additive commutative group structures on the type Z mod 37. And we've got a term of that type, which means basically that Z mod 37 is now a group. We've proved it's a group, and the fact that we've made this an instance. If I change it to def, let's still. Yeah, we don't ever use the fact that it's a. I'm telling the type class instance. There we go. I'm telling the type class inference system. Yay! Look, we've got another group. The type class inference system handles groups, but I don't. It looks like I don't particularly need to tell it that. Right, now multiplication. Let's zoom through this. So we've got to now prove that it's a ring, right? And what's the difference between a ring and a group? Well, a ring has a 1 and a multiplication. So 1 is obviously the equivalence class of 1. Multiplication is... Oh, apparently this is tricky. How are we going to do this? Well, this is all those intros, right? Intros, A1, A2, and then H, A, H, A. No, it's not intros, it's rintros. Rintros, and then B1, B2, BHB. And now let's have a look at this. So now, right, so A1 and A2 are congruent mod 37, and B1 and B2 are congruent mod 37. And we've got to prove that A1, B1 and A2, B2 are also congruent mod 37. So let's use, I don't know, let's use 53. That's not the right answer, but let's just see what we've got to do here. We've got to prove A1, B1 minus A2, B2 is 37 times something. And the way to do that, let me think. So it's A1 times B1. You do a trick, right? You do minus A2 times B1, then you add A2 times B1, then you do minus A2 times B2. This is kind of a cool way of doing it. So the left-hand side is this. And so the left-hand side you can write as A1 minus A2 times B1 plus A2 times B1 minus B2. And so now you see this. So the left-hand side is 37A. You see A1 minus A2 is 37A. So this is 37 times A times B1 plus A2 times 37 times B. And so we're supposed to be writing the left hand side as 37 times something. So I'm not going to use 53 anymore. I'm going to use A times B1. Sorry, I'm going to use A1. No, I'm going to use A times B1 plus A2 times B. And now this is slightly messy because again we've got this problem that we can't. What we need is a Gröbner basis tactic, right? That's what's missing. We need a ring tactic that uses hypotheses. Do you know, we just got some preliminary version of it, but I don't think it's, what was it called? Linear combination, I don't think, yeah, hard luck. Very recently, Mathlib got a preliminary version of such a tactic. However, it's not on the version of Mathlib that we're using for the course, and I'm not going to change the version of Mathlib because it will just cause more confusion than it's worth. So let's just do mull_add. Let's just do it by hand. Mull_add. And now what do we need? I need to get to 37 times A. Oh, I need to get to 37 times B. That's going to be hard to get to. Let me change B times A. Let me change A2 times B to B times A2. Then it's just going to be easier. And then we need mull_soc, right? It's mull_add. I hope you've played the natural number game. Mull_soc, and then mull_soc again. And there, and now we've got, you see, it's not, yeah, it's 37 times A, so now we can rewrite HA this way, and probably this way as well, probably HB. There we go. And now this is just something that's going to be true by ring. Great. So there's multiplication, and that's the notation for multiplication. And there's the fact that a multiplication of the quotient is quotient of the multiplication. And then let's go. So there's mullisoc, and that's going to be really similar to addasoc. Let's try the same proof. There, and it doesn't work because we don't want to sim with addasoc, we want to sim with mullisoc, and that has worked great. And then 1 mul is going to be the same as add 0, or 0 add. Let's try this one. That's done that. Left distrib, how many variables are involved? So that's 3 variables. So it's this one again. And that hasn't done it because I need left distrib here. That's done that one, and right distrib should be the same here, but sim with right distrib. You see what's happening is we're getting right distrib for the quotient by using right distrib for the integers. And then mulcom is going to be, there's 2 variables. Have I done a 2 variable one? Well, it's going to be addcom. Where's addcom? Here's addcom. Rotten luck. I don't have the intros. Oh, I missed one. I missed 1 mul. We're not finished yet. So this one needs to be intros, and then it was probably A and B. And then let's clear A and B. And the simplifier doesn't do it because it needs to know mulcom. There we go. And I thought I was done, but I randomly missed off 1 mul. Have we done mul 1? Yeah. We've done mul. I think I was doing 1 mul and I randomly posted the wrong thing. There we go. The simplifier knows 1 mul, so we don't need to tell it. And that looks like that's the end of everything. There you go. So Zmod 37 is a ring. You know, if you want to go crazy, you can try and prove it's a field. I mean, that's genuinely harder because you've got to come up with an inverse, and like the 3 doesn't have an inverse in the integers, so you've got to think a lot more carefully about how things are going to work. But I'm not going to say any more about that here. I guess to be quite honest, that would be a great thing for the number theory. Let's do that later on when we're talking about number theory, because this is all about quotients. Right, cheers, thanks for watching.